to my lecture today. I hope those online, can you hear me clearly? Sophie online. I need someone to confirm if you're hearing me. Okay, thank you so much for confirming that. Before I get started today, I want to make a series of announcements, and they are very essential. Of course, I'm still going to put that on the announcement section. You know, the reason why I also make announcements in class because my experience shows that some students don't check announcement section. The first announcement has to do with those who wrote exam online. That the exam have already been graded, and of course I've uploaded their grade. In fact, I even send their document to them electrolytically. So in case I made a mistake, you can check and get back to me. Those who wrote at DRC, I just received their exam document yesterday, and that will be graded today. Okay, I want to say the performance in the midterm too look better than what I observed in midterm one, because the performance now go to 90%. But we can make maybe the average now go to 90%. I want to say we can still make that average in the final to be 100%. If you can listen to what I want to say now. Do you know the final exam, we only cover 3 areas. I'm going to say that again. The final exam has a huge weight, and it's going to cover 3 areas. It's going to cover the areas that we've not covered in midterm 1 and midterm 2. And what are those areas that we're talking about? It's going to cover PCA. It's going to cover repeated measure. And it's going to cover the last topic, logistic regression. Does that make sense now? So which means things that we're doing newly is what the final is going to cover. I'm going to say that again. The final exam, we only cover 3 areas. The countdown to the final exam starts now. Okay. So it's going to cover 3 areas: the PCA, repeated measure that we've been doing, and the logistic regression. Does that make sense to everyone? That is the area the final we cover. 3 areas. I will repeat that again. Number 1, principal component analysis. Number 2, repeated measure. We're still doing repeated measure. We're going to finish this repeated measure on Monday, and we're going to start the last topic that we call logistic regression. So the final exam we cover only 3 areas. Does that make sense? And those are the areas we're doing newly. I want to welcome you once again to my lecture today. We are still on repeated measure ANOVA, but what do we want to do newly today? We want to focus on random intercept and random slope model. Let me tell you what we've done before now. We've considered a situation where we have a random intercept, okay, but the slope is not random. We are still assuming the same slope for all the subjects. Why the subject have different intercept? So what difference does it make? Do we stand to gain do we stand to gain in efficiency if we decided also to randomize slope across subjects, like making subjects to have different slope as well? Because what we assume before now is that the slope is the same, except that the intercept is different. And because of that, in the outline, I'm going to talk about random intercept model, like reviewing that with you, the random intercept and slope model. But let me tell you this. there are two versions of random intercept and slope module. Situation where we got two effects that are random. I'm going to say that again. Intercept random, slope random. We're going to consider possibility of them correlating. And we're also going to consider situation where they don't correlate, which means there are two versions of both effect random, whether the random intercept and the random slope. And we can use the idea of nested ANOVA tests that we've been using, that we use on Wednesday, to compare between modules, so that we'll be able to choose at the end of the day which one is okay. Even though in my research, I'm assuming random intercept and random slope, which module am I going to choose between when the two effects are correlated and when the two effects are not correlated? I'm actually going to walk you through that today. You know, when we're talking in statistical inference is about testing hypotheses and confidence interval. So confidence interval is not left out when we're talking about statistical inference. And that is the reason why, in addition to testing hypotheses, we're also going to look at the confidence interval. And that will also be done today. But before I go into that, I think I will need to tell you, practically speaking, what do we mean by random intercept? Like, for instance, if somebody, you know, I remember when I was in school, because my mother cannot write one. My mother, my own biological mother, okay, the best mother, that the person I call the best mother, she cannot even write one. Like, she's not educated. And whenever I read, whenever I study, I normally believe I understand what I've studied if I can explain to my mother in my language. She doesn't go to school. But my belief is, if my mother can understand me, anybody in the world will understand me. So what am I trying to say? If I want to explain, if my mother asks me, Kazim, what do you mean by random intercept? Do you know what I'm going to tell my mother? I'm going to say, okay, when you say random intercept, it means the individual that I'm using, okay, the differences in the individuals in the means across all conditions. Maybe the individual was subjected to different kind of conditions, and the individual that exists between these individuals in the means, MEANS, that's what I mean by random intercept. But if I talk about random slope, what does that mean? Oh, the individual differences in the effects of the explanatory variable, which means we have individual differences due to what? Effect of the explanatory variable. That's what we mean by random slope. So what we're trying to say, every individual, they're basically going to have different slope. If every individual has different slope, you know what that means? Then the effect of explanatory variable on the response is not going to be the same. Does that make sense to everyone? You know, I want you to be seeing what you are learning. When you see what you are learning, you'll be perfectly fine. Okay, now I've explained that to you now. Okay, based on feedback that I got yesterday, and I want to appreciate those who have been visiting me during my office hour. Some have been asking about, oh, how are we going to get a code? How can the data for question number 2? Of course, this is the code. You need to first load that package. Then you're going to have access to your data. Some students have been reaching out to me about data description, this and that. When you run that, you're basically going to see what you have in the explanatory variable, their names. Okay, so if you run that, now let's go into today's business, random intercept and slope model. Okay, now let me tell you, I can ask you to state a model. There's a difference between stating a model and stating the components in the model. If you take a look at midterm 2, okay, I also want to remind you, I've already posted the solution to midterm 2. Check the canvas. In case of in case you want to compare, your your own booklet with the solution that I provided. Now, there's a difference between stating a model and stating the component that we want to estimate in a model. If you take a look at what I presented to you now, did you say model? But when I ask you to state the parameter to be estimated in a model, maybe I need you to tell me the beta null, the beta 1, the B1, the B1, I2 that you're seeing on the board. And that will be the components of the model. Now, do you know when you are working with a random intercept and random slope model, okay, two effects will be random. And if two effects are random, we expect them to have variances, right? Not only that, we expect them to follow normal distribution. Take a look at what I have. The BI1, the BI2, they are the random here. Okay, that's why you are seeing them following normal distribution. The very first one is the random subject specific effects, and the second one is a random slope for each subject. The essence of incorporating random slope, we actually want to nullify parallelism. That's not like parallel anymore. Okay, every subject will have their own slope. Does that make sense to everyone? What I'm presenting to you now is the specification of, when you have a random intercept and a random slope model. And we're also going to have assumption around the residual, where the error follow normal distribution. Take a look at what you have now. Now, looking at the random intercept and the random slope model, you know what I'm trying to show you now. From the model, can we have a way to derive what the total variation is going to be? When I say total variation, I'm talking about the total variance, the variance of the system, the variance of the variance of the response. Okay? So what you're seeing me doing on the board now is to theoretically derive the variance of Yij. But do you know when you do that? Oh my God, take a look at what I'm seeing now. Before, there was nothing like covariance. You know why? Right now, you can say sigma B1, B2, right? Okay, you have the sigma B1, B2 could be 0 or not. When sigma B1, B2 equal to 0, it means the two random effects are not correlated. If the two random effects are correlated, we expect the covariance to exist. Does that make sense to everyone? Take a look at what I'm displaying now. And from there, I can also derive the covariance. Why am I interested in getting the variance and the covariance? Because we may also want to figure out the ICC, the intra-class correlation. Okay, of course, we're still going to make use of our package. Don't forget we're dealing with the random effects. So the method of maximum likelihood and the restricted maximum likelihood will actually be used. And if I want to compare between models, I'm actually going to use ANOVA function to do that, which we call the nested egg. Now, I need you to pay attention now. Everything that we'll be doing from now is going to be in the final. Okay, there are going to be three. For the final, we cover three areas: PCA, repeated measure, and logistic regression. We haven't done that. Logistic regression will be the last topic that we're going to do. Now, we started an example the other time that where we're using general data. We're actually looking at the effect of some explanatory variables on a distance. And that very distance is very, very crucial to, to scientists. I wanted to take a look at what I have right now. If you take a look at module _2, now I need you to focus now. I'm going to circle that. Now take a look at 1 plus H vertical bar subject. What do we normally have before? When we are considering random intercept, is only going to be 1 vertical bar subject. When you are using 1 vertical bar subject, that very 1 indicates intercept. It means you have a random intercept. But right now, in addition to intercept now, you also have H, which means you're talking about random intercepts and random slope. Does that make sense to every one of you now? I needed to look at the code. Statistics is very, very easy. All what I just need from you, if you don't understand, ask me question. You deserve to be served. You pay for the service. Okay, now, when you take a look at what I have now, okay, where we run it, let's see what we got. Of course, we're actually going to have a variance aspect, but I want you to take a look at that code, module _2. You actually have distance on H. There's a particular H that is fixed. Look at that. And there's another H that is random. So in the arrow output, we're actually going to have 2 versions of results, where one is going to be fixed, the other one is going to be random. Let's take a look at that. Now, do you see the first one? That is a random one. We started from here. We started from, look at that, random effect, variance. Okay. Now, the random intercept, the variance is 3.5502. Okay. The random effect of age, the variance is 0.0259. Please, I need you to focus now. There's a difference between variance and standard deviation, because in the midterm too, some were quoting standard deviation instead of the variance. There's a difference between the two when tested in variance, not the standard deviation. Okay, now, and of course, the first row is basically going to be the variance. And the 0.446 says that is a variance of residual, right? Take a look at that. Now, in case I ask you about the contribution of random effects, I'm expecting you to tell me what is the contribution of random effect of intercept, what is the contribution of random effect of age, what is the contribution of the that of the residual. Okay, those 3 are actually listed. 3.5502 is 0.0259 is 0.4466. Now, the other version of the results would be fixed, and that will be targeting age. As you can see, the last aspect of the result will be correlation of fixed effect that you can see. Another version of the result now is we actually want to look at what is a random effect of intercept and slope is actually here. Oh my God. Take a look at what I'm projecting now. The random effect of intercept is different. The values that I have is kind of different across the participants, and that of the age is different. Can you see that now? Then this guy here the next one I want to show now is this is not the intercept and age. This is just the random effects of intercept and age. But what is the real intercept and age is this guy here. You see that? We don't have the same slope anymore. We got different slope across individuals. You know, we're using 11 subject. I think this is the one that we were focusing on female. Let me look at the data. Look at that data F. Then we're only focusing on female here. That's how we got 11, right? Take a look at that. Now, let me see. Any question on what I've shown now? Any question? Any question on that? Do not hide your feelings. If you have a question, you ask me now. Okay? You're going to have this area tested in the final. Okay? It doesn't matter what you've done before. Right now, you need to be serious now. Okay? Because the final will only focus on principal component analysis, repeated measure, and logistic regression. In fact, tomorrow I'm going to upload the final practice questions. Wash out on the canvas. Final practice question without solution. That's what I'm going to do. Then next week, I'm going to upload the solution. Okay, now let's go to module 3. Well, in module 3, you know, when you take a look at module 2, give me 1 second, I think a chat came in. Somebody said we are estimated using ML, not that, but why we still use that command. Okay, we're still going to use that command. You know, there's a little difference between maximum likelihood and restricted maximum likelihood. So whether we're using any of that, we're still going to use LMER. So I believe I've answered that question. We're still going to use that in R. Okay? And if you need more clarification on that, so you can visit with me during my office hour. Thank you. Okay, so I want us to look at the next module. In the next module, we want to focus on, you know, the module 2, what we focus on was actually female. And we consider random effects of slope and the random effect of intercept. But right now, we are back at the general data. What do you have in the general data? You have both male and female, right? And the number of observation is 27. But what is module 3 telling me now? Module 3 is testing the interaction effect between age and gender, and why we want to use the random effect of slope. How do I know that it is the random effect, you know, of slope that I actually want to use? Because you can see age. You know, in this one, you can say 1 is missing, right? It doesn't matter. I'm still talking about it too. You know, in linear regression, at time when you are coding, okay, we may decide to put 1, we may decide not to put 1. Of course, arrow will automatically consider that you are fitting a linear regression with an intercept. Okay, now here we want to look at the effect of interaction, and at the same time we're using you know, random slope and random intercept. We estimate that. You can see in the random effect side, right? In the random effect side, you see the random for intercept, you see the random for age. Okay? And in the fixed effect side, I'm afraid you're going to see a lot. in the fit is a effect size. Don't forget, there's an interaction, age, gender. We can never have interaction without main effect. Before I can have interaction between age and gender, it means there exists the main effect of age, the main effect of gender. Before we talk about their interaction effect, take a look at what I'm going to have next. Oh my God, that is why I got age, gender, and the interaction effect. Does that make sense to everyone? Why are we having gender M? Oh, R as automatically coded male as 1 and female as 0. But just like what I told you the other time, coding one level of a categorical variable as 1 or 0 does not mean the one you coded 1 as a numerical advantage. No way. It's just for labeling. Okay, then we're going to have correlation of fixed effect, which is what is listed right here. Now, we want to go into another module now. What is it? If you take a look at, we've done module 1, we've done module 3. Okay. Now, module 1, we did not consider interaction in module 1. Module 1 has age. We consider interaction in both, as what you can see now. But except that module 1 is a random intercept module. Module 3 is both. I'm going to say that again. Module 1 is random intercept module, like it is only intercept that is random. Slope remain the same. But in module 3, both intercept and slope are random. Do you know in statistical analysis, we may be faced with the problem of choosing which one is better? I got 2 modules in one, and don't forget, I'm looking at I'm still investigating effect of interaction. If you take a look at I'm going to circle that for those online. Now, for those online, and for those of you in class now, look at module 1. You can see age multiplied by gender, right? If you take a look at module 2, you can also see age multiplied by gender, but the difference between the 2 modules. In the first one, you have one vertical bar subject, right? The one vertical bar subject is a random intercept. The other one is the age vertical bar subject, that is random intercept, random slope together. Now, what are we going to use to choose between these 2 modules? We're going to use nested ANOVA test. So it's going to be ANOVA. In parentheses, I'm going to tell you what you're going to put in the parentheses. In the parentheses, the first module will be simpler module. The second one will be complicated module. Let me tell you now, a module with a random intercept only is simpler. But a module with both random intercept and random slope is complicated. So that when you are testing under your HO that I call non-hypothesis, the non-hypothesis will support the simpler module. The alternative hypothesis will support the complicated module. Does that make sense to everyone? Now let's look at the p-value now. The p-value is 0.6593. That is greater than any reasonable level of significance. Let's use 0.05. When the p-value is greater than 0.05, what are you going to do? We're basically going to fail to reject HO. When we fail to reject HO, what does that mean? It means the model that the model that has random intercept only is the preferred model. Does that make sense to everyone? If a model with the random intercept only can do the job, why do I need to go for complicated model? When you go for complicated model, it's like you want to use sorry, I'm sorry to use this example. You want to use bullet to kill mosquito. You know mosquito? Okay, you use bullet to kill mosquito. Why? If a simple model can do the job, why do I need to go for complicated model? So that's what we've decided here. Any question? Now I quickly want to go to another example now. Oh my God, this example is very, very interesting. Sleep study example. The data represent the average reaction time in milliseconds per day for truck drivers in a sleep deprivation study. Okay? Okay, on day 0, the subject had their normal amount of sleep. Of course, everybody knows those who drive truck that go from maybe Chicago to Minneapolis, or they're doing a very great job because they are helping our society, and some of them don't sleep. So that's why when you see them, you give them kudos. They're doing a great job. Now, starting that night, they were restricted to 3 hours of sleep per night. The observation represents the average reaction time on a series of tests or given each day to each subject. The 20 subjects were measured for 9 consecutive days. Okay, that's according to Bill and Key et al. 2003. If you want to have access to that data, this is what you're gonna load. I quickly want to go into. So what do we want to do now? Level of us have a plot. When Mattia is gonna walk you through all of this in the lab. Now, what is this showing? This is trying to show for each driver, okay, the plot. Let me like a scatter plot of the average reaction time against the day of sleep or deprivation. Of course, as you can see, you don't expect to have the same slope here. I can see some is looking like a curve, some is looking like a straight line. Descriptive statistics, when you want to conduct research before you go inferential, I will advise you always before first go descriptive. You explore your data. Part of exploring data is when you have a kind of graphical, when you start, looking at the relationship graphically, where you're going to have a sense of whether you actually going to fit the same slope or different slope for subject. As you can see now, there, so take a look at that. Now, let me tell you this. When you are working in this area, you need to first start with random intercepts. The random intercept only is the simplest model that you can first think about. Do you see the code model 1, where we're looking at the effect of days? We are looking at the effect of days on reaction. Why we're using random effect for the intercept? Can you see that? In the end, of course, you can see our result, the usual result that we normally have, where we're going to have the random effect side, we're going to have our fixed effect side. Okay, we've already done that now. Now, another model we can think about is, okay, I've considered random intercept, but looking at the descriptive statistics that we did, this is giving us a sense that using the same slope for all the subjects may be misleading. Okay, and we need to incorporate a random effect of slope as well into the model. So when I do that, that's exactly what I'm doing here. Look at that, random intercepts and slopes. Okay, making how many models now? The first model was random intercept model. The second one now is both intercept and slope, are randomized. Of course, you already know the code. I have my result. Now, if I got my result now, the next thing I need to do, I got 2 models before me. I need to take a decision. I got a model with intercept being random, and I get another model, both intercept and slope are random, I need to choose the best out of them. That is exactly, for those of you online, that is what I'm doing here. For those of you in person, that is what starts from ANOVA into model 1, model 2. Anytime you do ANOVA into model 1, model 2, you are actually conducting, you are conducting what I call a nested ANOVA test. Nested ANOVA test is for you to be able to choose between two modules. Don't forget, the very first module you're going to write will be the simpler module followed by the complicated module. The simpler module is a module with a random intercept. The complicated module is a module with both random intercept and the random slope. Oh my God, in the null hypothesis actually favor the simpler module, the random intercept module. The alternative favor, both, intercept random and slope random. Take a look at the p-value now. What would be my decision? The p-value here is very, very small. Look at the p-value. When p-value is less than level of significance, the standard one we're using is 0.05. We're actually going to reject HO. Rejecting HO, my God, you are rejecting the simpler module. You are now going in favor of a complicated module. What is a complicated module? The complicated module now is a module that have random intercept and the random slope. Do you know, I knew from the beginning when I did my data exploratory analysis, I'm going to show you now. Do you know I knew from here? Merely saying this, I know that we never have the same slope. And the statistical test that I conducted now, just confirmed that for me. Any question? Any question? This final should be walkover for you. The final should be walkover. Okay. I know some of you are ready today. If I say, okay, final is going to be today, I know you guys are ready. Okay. But if there's anyone struggling, please make sure you let me know. Okay. Now, do you now know what I want to do in the next 10 minutes? Let me tell you this. I've compared a model with a random intercept with a model with a random intercept and random slope. And we actually concluded, we choose the one with both random, but that is not all the time. That depends on your data, that depends on the result of your test. But do you know, we can also make a distinction between two modules. The two modules, they have their intercept and slope random. But what is the difference between them? One is one in one, they are correlated. In the other one, they are not. I'm going to say that again. Statistical analysis, what we do in statistics, like I used to say, statistics is more or less like a story. Do you know when we compare random intercepts with a random slope, random intercept with a random intercept and slope together, we actually concluded in favor of the complicated module, which is the random intercept and the random slope. But that is not the end of the story. Do you know within the random intercept and random slope, we can also compare the one where the two random effects are correlated, and the other one where the two random effects are not correlated. Because when you have two random effects in a model, there is tendency they're going to correlate. Take a look at what I'm showing you on the board. Random intercept and slope uncorrelated. What am I going to show for uncorrelated? Oh my God. Take a look at the code. I added 0. I want to see if you have spotted that zero. I need a thumbs up from you on the board. Okay, you've seen zero that I had it, right? Is zero plus days, right? Okay, vertical bar subject for those who are online. I'm going to circle that here. Now, do you see that? Okay, now I had a zero. Is zero that I had there means uncorrelated. Is zero means, or when two variables are uncorrelated, what is the correlation value? Zero. Does that make sense? That was why we had a zero. Now, when you had a zero, we're going to recompute. Do you see that now? Okay. Now, when we compute, we get this now. Then we're now going to go to another. Give me 1 second. Okay. Now, the one we did before this one, the one we did like this one, like this one. Okay. This is the one, there's no zero, right? Do we put zero? No zero. This is a correlated one. Now, the one with zero is a correlated one. You know what we can do? We can also do ANOVA test to compare the two. Which one am I going to choose? If I know that model with the random intercept and the random slope is good, but I have two versions of them. One, in one model they're correlated. In another model they are uncorrelated. Now I'm going to conduct my ANOVA test again. Oh my God. Let me tell you this. If I'm conducting my ANOVA test, which one is going to be the simpler model? Because the simpler model will be the one in the non-hypothesis. The complicated model will be the one in the alternative. Okay. Now, the one I'm going to put in the non-hypothesis will be the uncorrelated one. Does that make sense? The uncorrelated one. The uncorrelated one you can see now is the one that has zero. The correlated one will be in the complicated model. Oh my God, take a look at the p-value at the end of the day. We fail to reject the non-hypothesis. Failing to reject the non-hypothesis, it means you are using a model that have both random intercept and random slope, but uncorrelated. Statistical story is very, very sweet. When you listen to the story, you want to listen to more story from statistics. Can you see that? And that was why I said, since there is no statistical difference between the model with the correlated random intercept and slopes and uncorrelated random intercept and slope, then we choose the model with uncorrelated intercept and slope based on parsimony. What do we mean by parsimony? Oh, parsimony. It means we're going to have few parameters because we're choosing the simpler model. The complicated model, we have more parameters than the simpler model. Does that make sense to everyone? Okay, I'm going to go to the last one now. Confidence interval. Okay, the same thing that we do with the hypothesis testing, we do confidence interval. They have to agree. Now, what am I doing now? I'm doing a confidence interval for random intercept. Okay, for random intercept, I'm doing confidence interval. So let's see results. Oh my God, take a look at that. What result are we seeing now? That's a confidence interval for what? For sigma 1, for sigma, for intercept, for age, for gender M, for the interaction. I wanted to take a look at that. So these are the confidence but let me tell you this. The confidence interval, when you take a look at what is listed, we have some that are fixed effect. There are some that are random. The sigma 0, 1, the sigma and the intercept, okay, all those, if you take a look at that, they are all random. Okay, now this is the confidence interval, for that. Now we can also do the confidence interval for the other one. What are we going to do next? Oh my God, what we're going to do next is going to be assessing model absorption, because everything that we've been doing in repeated measure, the result can only be trusted if error behave well. What do I mean in statistics to say error behaves well? In every statistical models are very, very great. They look beautiful because we have a way to validate those models. Do you know every statistical model has error components? Okay. Now, the error component that we have in every statistical model, okay, all assumptions around, the model revolve around the error time. Now, I'm going to say error behaves well if all assumptions are met. If there's a violation of assumption, even if you get a beautiful result, that result can never stand the test of time. And that is the reason why what we're going to do next, which is going to be the last class for repeated measure, we'll be assessing model assumptions before we can report our results. Before we can actually say, okay, this result is looking promising, we have to assess the model assumptions. This is what I used to say. What happened in the court of law also happened in statistical analysis. If somebody commit an offense in the state of Chicago or in the state of Illinois, let's say Chicago to be precise, that person should be tried under the state of Illinois law. If the person is being brought to Minnesota to try, Minnesota does not have a territorial jurisdiction. Even if the court in Minnesota was able to establish the fact that the person committed the offense, if the nature knows the truth, nature always knows the truth. If the person committed the offense and the Minnesota court was able to establish that, whatever decision they take in Minnesota court will be declared null and void because the Minnesota court does not have a territorial jurisdiction. So also in statistical analysis, even though your p-value is great, you have a significant result, everything looking so promising, but assumptions are violated. I'm sorry to say it's going to be an exercise in futility. It's like you are taking a case out of its territorial jurisdiction. Even though your model is looking promising, but the facts remain, assumptions are violated, then the method you are using is not going to it's not going to stand a test of time. You're actually going to mislead. And that is why what we want to do next is very, very essential, assessing model assumptions in a repeated measure ANOVA. Any question before I go today? Any question? It's another weekend. I like the weather today. I hope you're going to enjoy your weekend. See you on Monday. Bye for now.